Okay, we're going to do the notes starting at 10, but I need you to move back to page 7. I told you something incorrectly, and this is going to be important by the end of this lesson. So for number 2, I had told you this was sometimes that a rotation image actually always has the same orientation as the pre-image. I'm going to show you the difference between a rotation and a reflection. For a rotation, when you rotate, like I drew here, if I read the letters starting at A going clockwise, it goes A, B, C, D. Okay, after the rotation, if I start at A and read the letters going clockwise, it goes A, B, C, D. But in reflection, it's not the same. So you'll see the pre-image, it's still A, B, C, D going clockwise. But if you start at A after the reflection, this is like I reflected over the y-axis. If I go clockwise around the square, I'd go A, D, C, B. So it's not the same orientation. It's switched where the letters were. Okay, so for a rotation, it will always maintain the same orientation. But for a reflection, it is going to change the orientation. Okay, so now back to page 10. Bottom of page 10, we're going to start talking about rotational symmetry. So I wrote what that means up here. It says when a figure can be mapped into itself by a rotation of 180 degrees or less about the center of the figure, and that center is called the center of symmetry. So imagine this pinwheel. This is the pre-image right here. We haven't changed it at all. That's why it says 0 degrees at the top. It has not rotated at all. All three of these are options for what you could get after a rotation. So you'll see after a 45-degree rotation, this is not in the same position as our pre-image. So it does not have rotational symmetry at 45 degrees. But at 90 degrees, you'll see if we rotate counterclockwise 90 degrees, this pinwheel looks exactly like the first one. So there is rotational symmetry at 90, and then the same at 180. It has rotational symmetry at 180. Now you might see that you could rotate it 270 degrees and also get the same image, but in the definition here, we want anything that's 180 degrees or less. Okay, so after 180 degrees, it doesn't count. It's because any multiple of 180, if I do 180 times 2 is 360, and then plus another 180 is 480, no, 360, 540, sorry. If I rotated this 540 degrees, it would go back to having rotational symmetry. Any multiple of 90 or 180, it'll have that symmetry. So 270 is 90 times 3, so it's just a multiple of 90. Okay, so let's go to the next page. We have to figure out what's the rotational symmetry of these figures. So for a parallelogram, we want to figure out if it has rotational symmetry. And the easiest way to do this, if you're not sure, because to me I'm like, okay, if I rotate it, will the parallelogram still be moving up and to the right? You can flip your paper. So I'm going to rotate my paper counterclockwise. If I go 90 degrees, it's not going up and to the right anymore. If I go 180 degrees, it is going up and to the right. So this one will have rotational symmetry at 180 degrees. Okay, the regular octagon is the hardest one on here, so we're going to skip it for now. The trapezoid, you'll see it has the small part on the bottom and the big part on top. If I turn it, it only has that small part on the bottom and the big part on top when it's facing this way. So this one has no rotational symmetry. Okay, and on the bottom there are 2 answers that have no rotational symmetry. Can you tell which ones they are? It is both of the triangles. So I'm just going to put empty sets for both of those instead of keep writing no rotational symmetry. There is no answer. Okay, for this hexagon, it has 6 sides, so it's a hexagon. You might at first think, no, that won't work. But if I turn it upside down, you'll see it looks like a rectangle with cuts out at the upper right and the lower left. I'll turn it this way. still upper right and lower left. So this one, if I turn the paper upside down, so that's 180 degrees, it'll have rotational symmetry. Okay, so the octagon is very much like when we were talking about rotations. I could draw in the center of the octagon, and if I connect to all the vertices of the octagon, you'll end up making 8 triangles. So you can take your 360 and divide it by 8, and you'll get 45 degrees. So I can move this octagon just 45 degrees, and it'll map each vertex onto the next vertex. So every single vertex around here would just map onto the next vertex. So 45 degrees is your first answer. And if I do 45 degrees twice, I'd end up 2 vertices away, so that's 90. And if I do 45 3 times, I'd end up 3 vertices away, 135. And if I do it 4 times, and end up exactly across this diagonal, that will be 180. And we don't need to go past 180. Okay, so for example 11, this did not copy very lightly. It's very dark, but this is lampshade. It's kind of an accordion lampshade. We want to figure out if the lampshade has reflectional symmetry or rotational symmetry or both. So we're going to do true or false. So we are only looking at the lampshade. We don't have to look at the whole lamp, but actually all these answers are the same if you look at the whole lamp or the lampshade. So the first one says a plane that is parallel to the top of the lampshade, so that's going to be horizontal, and passes through its middle, so that's about right here, divides the lampshade into 2 congruent parts. Well, that's false because the top of the lampshade is smaller than the bottom, so this one is false. A plane that is perpendicular to the top of the lampshade and passes through its middle divides the lampshade into 2 congruent parts. Well, that one is true, because if I put a vertical line through it here, it will make kind of a half trapezoid on this side and half trapezoid on that side. So that one's true. C, the lampshade can be rotated about a horizontal line so that it matches perfectly. So if I draw a line here, if you rotate along that line, it's going to flip the lampshade upside down. So that is not going to work. But the lampshade can be rotated about a vertical line so that it matches perfectly. So the lampshade is kind of a circle. If you imagine putting a line straight through the middle of the lampshade, so it goes through the lamp or the light on the inside, and rotating the lampshade around, it will line up perfectly. So that one is true. So it has a vertical line of symmetry, and it has it has a rotational symmetry around the vertical line. Okay, so the next page is completely practice. I would like you to pause your video, do the entire back page, and then come back. Oh, and the page after that. Okay, so number 1 says circle the center of rotation for the transformation at the right. It's got to be C, because C prime landed on top of C. If they are right next to on top of each other, it didn't move when it rotated, so it has to be C. 2, if the center of rotation of a figure contains the point Y, then SY prime is the same thing as SY. That was in the definition or the key concepts for rotations. Okay, and so for A, since cross out the point for which A is not the center of rotation, this is the only one where A is the center of rotation. You'll see that this point on one lightning bolt is the same point on the other lightning bolt. This one had a bit more work. So you'll notice, though, when you do the rotation and the reflection, you end up with the exact same triangle over here. You'll see you use the exact same points, just for different letters. So this is where I was talking about the orientation matters. And so I started by crossing this off, because I made that mistake earlier, but then I said, no, we're going to fix it. So for both of the transformations, the size and the shape of the triangle did not change. But for the rotation, that was the only one where the orientation stayed the same. So if you look at these, if I go clockwise starting at the R, I'd go R, S, T. Okay? If I go clockwise starting at the R prime, goes R prime, S prime, T prime. So the orientation didn't change for the rotation. But for the reflection, if you start at R prime and go clockwise, it doesn't go to S next, it would go to T. So that's where the problem is. So I wrote that kind of down here in my own words. Both are isometries, which means they're rigid motions. We have a congruent triangles. We made the exact same size and shape of triangle in the pre-image and the image. The reflection changes the orientation of the vertices, and the orientation stays the same with the rotation. Okay, our last page. So your friend thinks that the regular pentagon in the diagram at the right has 10 lines of symmetry. Explain and correct your friend's error. So we're going to put a check next to the correct statements and an X if it's incorrect. So each line of symmetry bisects an angle of the pentagon. So if I look at this, this goes through an angle of the pentagon and out looks like the midpoint of the opposite side. Yep, that goes through an angle and a midpoint, angle and a midpoint. So I think this one is true. So we're going to put a check mark. Each line of symmetry bisects a side of the pentagon, and I said that because it looks like it bisects an angle and goes through the midpoint, so I think that's true. Each line of symmetry is parallel to another line of symmetry. I don't think there's a single parallel line in this whole thing. Nope. So we're going to say that is not true. Okay, the pentagon has 10 congruent angles. That's not true. There's only 5 sides, so there's only 5 angles. Pentagon has 10 congruent sides. Nope. The pentagon has 5 congruent side angles. That is true. The pentagon has 5 lines of symmetry. That is true. So each line of symmetry goes through one angle and one side. One angle, one side. One side, one angle. Well, there's only 5 angles and there's only 5 sides. So they counted their lines of symmetry twice because they counted all the ones that went through the angles, then they counted all the ones that went through the sides. But every single one goes through both a side and an angle. So I'm going to put they counted each line twice. Okay, use the regular pentagon below. Draw each line of symmetry in a different color. And okay, so I'm going to put, there's one here. There's one here. There's one here. There's one here. Of course, I'm out of colors. Let's see here. Oh. Then there's one here. Okay, so you should have, there's 5 different ones. That is the same picture as what we have up here. So that's all there is. There's 5.